Okay, so now we're going to apply these concepts of mutual inductance to the transformer. If I can write on the screen, the transformer. So a transformer's device, it takes advantage of this concept of magnetic coupling to kind of pass power through from one inductor to another inductor. Transformers are used in both communication circuits, they're used in power circuits. In communication applications, transformers typically used to do impedance matching and to eliminate DC signals from portions of the system. And in power circuits, transformers typically are used to establish alternating current and voltage levels that facilitate efficient transmission, distribution, and consumption of electric power. We're going to analyze what's called a linear transformer first, which is formed when two coils are wound on a single core to ensure magnetic coupling, so as we just kind of showed. And what we're going to write first is the complete circuit model for the transformer. So what we have is we've got some sort of source voltage. This is what we connect to the transformer, and that source voltage is going to have an internal impedance associated with it of ZS. We'll give that source voltage a name, we'll just call it VS. It then connects to the transformer at the nodes A and B. So now we're drawing the transformer. We've got a resistor and a inductor. So the transformer is modeled by a series resistance and a series inductance L1. I'm going to go ahead and give this a dot up the top. The secondary side of the transformer also has a inductor. It is then connected to a series resistance R2. This is L2. I'm going to give it a dot here. We then connect the output of that transformer to a load device. So the transformer exists basically inside this box. And there's, there's a mutual coupling that we talked about right there. So again, we've got some sort of voltage source. It's got an internal impedance. It's connected to what's called the primary side of the transformer, and then the mutual inductance couples whatever's going on in the primary side over to the other side, which is called the secondary side of the transformer. R1 is therefore given the name primary winding resistance, and L1 is primary winding self-inductance. Similarly, R2 is called the secondary winding resistance, and L2 is called the secondary winding self-inductance. And then finally, the last term we have there, M, is just called the mutual inductance of the transformer. So basically what we need to do is we need to apply the mesh current analysis to this transformer model. So what that means is that we've got two currents that are going to flow, two mesh currents. So I'm just going to draw a current here, I1, and another current that flows here, I2. So if we sum the currents around the primary side, or the voltages around the primary side, we've got VS, we've got a voltage drop across the ZS term, across the R1 term, and across the reactance of L1. So that's going to be I1 times ZS plus R1 plus L1. And then we have the voltage drop associated with the mutual inductance. In this, we see that the reference current I2 leaves the positive terminal. That means the voltage induced in L1 due to the mutual inductance M is negative here. And so we have to subtract off J omega M times I2. Looking at the secondary side, there is no voltage source, so we say 0 is equal to, we've got I2 times L2 plus R2 plus ZL. We then have to account for the voltage induced in L2 due to the mutual inductance. We see that I1 enters the positive terminal of L1, therefore we get a plus minus here, which is opposite of the other ones, so we have to subtract that off J omega M, and it's induced by current I1. So those are the two equations, the two mesh current equations that describe the circuit. Very often the term inside the parentheses here is just labeled as Z11, and very often the term in these parentheses right here is labeled Z22. Z11 is called the total self-impedance of the mesh containing the primary winding, and Z22 is called the total self-impedance of the mesh containing the secondary winding. So this is done mostly to be able to write simplified mesh current equations. If we were to solve Vs equals Z11 I1 minus j omega m I2 and 0 times I2 Z22 minus j omega m I1, if we were to solve those simultaneously via substitution, the result we would get is I1 is equal to Z22 over Z11 Z22 plus omega squared m squared times Vs, and we would find I2 is equal to j omega m over Z11 Z22 plus omega squared m squared times Vs. You see the similarities in these two equations. That allows us to simplify this as j omega times m over Z22 times the quantity I1. If we were to look at this whole circuit from the perspective of Vs, we see that the total circuit impedance, Z total, is just going to be Vs over I1. So I'm going to go ahead and do that math down here. Z total is Vs over I1. That's just telling us really what's the impedance of the circuit from behind these terminals, kind of pointing in that direction. Z total. And so I'm going to take Vs, I'm going to divide it by I1. I've solved for I1 right there. That's Z22 over Z11 Z22 plus omega squared m squared Vs. And notice that the Vs's cancel out of that, and I just flip this and I get equals Z11 Z22 plus omega squared m squared over Z22. I can simplify this by canceling out the Z22's. That's equal to Z11 plus omega squared m squared over Z22. If I go back and I look at my transformer model, the total impedance of the transformer is just the impedance between nodes A and B here, which is equal to ZT minus ZS. So ZAB, which is the transform impedance, is going to be equal to total impedance minus ZS. So what I would get in result for that is I get this total impedance, Z11 minus omega squared m squared over Z22 minus ZS. And what I need to do then is go find my formulas for Z11 and Z22, which are right here. So Z11 is just, again, ZS plus R1 plus, oh goodness, I left off the j omegas here. J omega, right? Those are reactances. Those need j omegas in front of them. Hopefully you guys caught that and are smarter than me. So I need to go ahead and do that substitution there. So that's going to be equal to Z11, which is ZS plus R1 plus j omega L1 minus omega squared m squared over Z22, which is R2 plus j omega L2 plus ZL. And I need to subtract ZS off of all of those. And what that results in is the ZS's cancel here, right? And I'm just left with ZAB is equal to R1 plus J omega L1. I've forgot a plus sign here. Plus omega squared M squared over R2 plus J omega L2 plus ZL. So this formula here gives you total impedance of the transformer.